Jeff has got some issues today, so I'll just go ahead and record a brief update on some of the activity that I've been working on. As a reminder, um, both Jeff and I are focused on trying to automate our tractors, and we're using this lawn tractor as a test bed to get all the sort of mechanics and software right. Basically, recently I've been working on path planning, and what I've ended up doing is creating a Jupyter Notebook, and I'll start with the end in mind. Scroll down here. What you see here is 5 outer rings of a particular location, and then what I'll just call stripes going back and forth, and you can sort of make out the U-turn that's at the end of each stripe. Now, there's different names for both those stripes and the U-turn, but I'm not going to bore you with that. Effectively, this Jupyter Notebook is a multi-step process that I go through in order to create both those outer rings and those stripes. Over time, I'm sure I'll be able to dwindle this down because it's still rather clunky, but it is at least repeatable at the moment. And while I'm still here, I'll just tell you that this circle here represents an obstacle, and having that path come down to that into that circle is a problem, and that's still, I've got code to fix that, but I've not incorporated that into this Jupyter Notebook yet. All of this, by the way, is up on our GitHub repository. So there's 3 primary steps. One is to create the lawn positions of the outer perimeter. You might guess that that's fairly straightforward. You go drive the property and save the ROS bag files. I'll add more detail about that a little bit later. So at the moment, I just summarize that to say, drive the property, save the ROS bag. You also have to drive around obstacles and use that ROS bag data as well to get the center point and the radius of that obstacle, or the circle that we're going to draw that represents that obstacle that you don't want to go into. So then you begin the process of creating the outer ring. There is a location database that's used to keep track of some key data around each of the locations. The notion is there would ultimately be multiple locations that you have to drive, and there's things to save, like how many paths do you want to run on the outside and whatnot. And so that goes on to running this particular Python script, which will then generate the first of many files to use to continue the process. When you use it in Jupyter, as you might know, you get some output from the program. This is just debug, I'll call it debug comments, in order to keep track of what's going on. But ultimately, this text file is created that can be fed into Pure Pursuit. Now, that is just the outer ring. That doesn't create the stripes. The stripes, those steps are here. I've just segmented this in Jupyter to say, here are some key variables to use. And so you run that, and then so all of that, those variables are made available to the subsequent cells that you run. This is just reading a polygon for visual confirmation. It'll create this diagram based on the data that I've fed it. And then to create the initial stripes, you run this script and you'll get an output that looks like this. Now, one thing to note is my cutting deck is 42 inches at the moment. Up here, I set the cutting width to 0.9 meters. That is used to create these stripes. These stripes happen to be double that, and the reason I did that is because it makes some of the math easier later to calculate the U-turn points. Visually, when you create this, because I have these indentations here, you get some multi-line segments, and I want to trim those multi-line segments off and only have these long unimpeded segments. So there's some simple data cleansing going on to cut those line segments out. This is what those line segments look like after the multi-line segments have been trimmed. Then the next step is to generate these points that are used for the turnaround points, or the U-turns, or the Dubin's curves, whichever language you are comfortable with. And this is a script that just shows some of the logic to do that. Basically, what I have to do is create a right triangle with the hypotenuse of the line on both sides of this line, and sort of to get your head around that, got that sample code in there, but the code is then repeated a little bit later to create these line segments. So earlier there were, I think in this particular plot, 23 line segments. Now I've created the turnaround points and created, line segments that are 0.9 meters apart. Now that I've got those line segments, I need to calculate the angle between those points, add a look ahead and speed, because the pure pursuit program needs all of that data in order to operate. So that code does its thing and generates a file. That the Dubin's shortest path library can use. So step 11 is about using that to create those, what I'll call U-turns based on a turning radius and the step size, because I'm also adding the look ahead there and speed. Those variables are hard coded into that. Generates then this file, and then to visually check that, I have this process to visually plot those. So now you can see those line segments with the U-turns on each of those. So at the beginning in step, Roman numeral 2, we created the outer bounds. This is Roman numeral 3, the output of Roman numeral 3, which creates the stripes. And visually check that together. There's some code here that shows the two of them combined, which I showed earlier. So anyway, that's where I'm at the moment. There's still considerations to be made on all of this code, namely, got white space here that needs to be filled in, white space here that needs to be filled in. I got to deal with this circle, but that's my progress so far.